Hello everyone. We are going to start into Module 6 with Section 6.1. This is one of the sections that we'll be covering in a few videos. So in this first video, we are going to talk about waves. So the learning objectives here: explain the basic behavior of waves, including traveling waves and standing waves, and describe the wave nature of light. So let's go ahead and get started. Just as a little bit of a preview for how we're going to go forward with this, there were some about 100 years, a little over 100 years ago, there were some changes to the way we understand waves and particles, and that's kind of one of the big ideas in this section. And we're going to start by just talking about what waves are. So we'll talk about waves in this video, and then we'll talk about some of the challenges to the wave idea in forthcoming parts of that. So this first chunk is sort of a preview of that. I am going to talk about electromagnetic radiation. And we're not going to get into all of the details of what that is. Because then we'd have to talk about magnetism, which is a fairly complicated idea. It's essentially a disturbance in the electromagnetic field that travels as a wave. So you don't have to know what the electromagnetic field is, just that we're going to be looking at things that are like waves traveling through there as a disturbance. Let's go ahead and talk about waves, and then we'll come back to that. So a wave is sort of a disturbance or an oscillation within some medium, and it propagates from one point in space to another. So it kind of travels along. I think we all kind of know what a wave is. So if you think of sports games where people stand up and sit down, that's a wave. The people aren't running around in a circle. That's a different thing than a wave. But they stay where they are, and they kind of move. So the medium itself is not moving. The people are not moving. The movement is traveling through the people. So that's essentially what a wave is. There's things that we can characterize about a wave, and we're going to talk about those. One is something called the wavelength, and we use the Greek letter lambda, lowercase lambda, to indicate wavelength. The lambda is the one that looks like an upside down Y. That is simply a measure of the distance between similar points of the wave. So between the high point of a wave and the high point of another wave, or even between the low point of a wave and the low point of the next wave. So we're showing some examples of some wavelengths here. So lambda 1, lambda 2, lambda 3. You can see that they can be different from one to the next. Another thing we can talk about with regards to a wave is something called frequency. Frequency, we use this Greek letter nu, which kind of looks like a funny V. If you end up drawing it and it looks exactly like a V, that's fine, as long as you know what it is. Frequency is a measure of how often a wavelength goes by. So looking at these examples down here, we go from one peak to the next. So that's one wavelength. That's another wavelength. That's 3 wavelengths. So it went 3 wavelengths in the period of 1 second. So we would say it has a frequency of 3 hertz. So hertz, in addition to being the name of a rental car company, is the unit we have for frequency, and it's cycles per second. So how many things happen in a second? You might be thinking about hertz all of a sudden, and you think of all these other places like radio stations that use hertz in some way, and that is actually what's going on there, as we'll see. And you can see as we are changing down here, if we change the wavelength, we're changing the frequency. They're related to each other, and we'll develop that idea here shortly. And then a third one, and it's not one we'll focus on too much in this course, but you might see it come up in a physics course, is the idea of amplitude. And amplitude is a measure of how large the wave is. And we actually will kind of address it a little bit, but we won't focus too much on using the term amplitude to describe that. Okay, so it's how large that is, or how big the disturbance is. So if you have, a wave at a sports stadium and people just raise their hands, that's, one amplitude. But if they stand up and raise their hands, that's a higher amplitude. So we can use that analogy there still. So it turns out for electromagnetic radiation, there is one thing that is always true, and we'll see there's lots of different possibilities here. But what's always true is that in a vacuum, that propagation of the wave occurs at a constant speed. Okay, we call that the speed of light, and that is shown here. So about 3 times 10 to the 8th meters per second is the speed of light. And it turns out that if you take the wavelength times the frequency, so wavelength would have units of distance, frequency has units of inverse time, then you get the speed at which the wave is traveling. Okay, for some waves that is a constant, specifically the speed of light, that's a constant. For other waves, it is not necessarily a constant. For this course, the only wave we really care about is the speed of light, or is light waves. So the speed of light being this constant is going to be an important thing to know, and we'll be using it as you'll see. Okay, so the electromagnetic spectrum is basically anything that travels at the speed of light through the electromagnetic field. And that turns out to be a lot of different things that you might already be familiar with some of them. And the difference between those is basically their wavelength and frequency. Those two things, again, are kind of changing together. And the relationship there, and you can kind of see that from this equation, is that as one of those goes up, so as the wavelength, for example, goes up, the frequency will go down. So it's an inverse relationship. And we'll see that as we look at some examples. So here we're showing, this is called the electromagnetic spectrum. We'll come back to the energy a bit later, so don't worry about that. But you'll notice there's a trend here in frequency and wavelength. So again, as one goes up, the other goes down. As you increase the wavelength, you are decreasing the frequency. As you increase the frequency, you are decreasing the wavelength. So at a very, let's start with a high wavelength. So when I said hertz and I said you might be thinking of a radio station, that's exactly what's going on. So radio waves are a form of electromagnetic radiation. They have very large wavelengths, so wavelengths on the order of the size of a football field. And when you're talking about the radio station number, that is referring to either kilohertz or megahertz in terms of frequency. So that is one end of the spectrum. So high wavelength, low frequency. And then as we move in this direction, we get into cell phones, radar, wireless, and microwaves are in this region. Microwave ovens, I should say. In terms of the microwave oven, I guess we can talk about that right now. The way that the microwave oven is working is that it is causing water molecules specifically to rotate. So the wavelength of the microwave oven is designed to cause water molecules to rotate, and when they rotate, they heat up, and when they heat up, your food heats up because your food is full of water. So that's kind of why they work. And as we move from this, we move into the infrared region. And in that region, we think of things as being what we experience as warm. And so there's a vibration of molecules that emits heat in that region. So that's why we experience that in that way. And then there's this very small band of what we call visible light. So this is a region where our eyes are able to interpret the electromagnetic radiation, and we do a really good job of it. We can see, for example, different colors very well within that range. Beyond that, we have the ultraviolet, and so when you think of that, you might think of damage to your skin from the sun, from being in the sun too long, and that's what that is. Then we get into X-rays, and then we get into gamma rays. Now, one thing you might have noticed as we've kind of moved through these different types of radiation is things tend to get maybe a little bit more what we might call dangerous on this end of the scale compared to this end of the scale. And there's a reason for that, and we'll come back to that reason a little bit later in a future video. So there's an example here of doing a calculation using this equation for the speed of light. So you should be able to do a calculation to find either wavelength or frequency. If you're given one, you should be able to find the other from this equation. So make sure to get some practice with that. And then I want to talk about a few properties of waves that will end up being important as we discuss how this relates to electrons. One of those is something called an interference pattern. So an interference pattern is when waves kind of overlap each other. They can do it in two ways. They can kind of add together and make a bigger wave, or they can cancel each other out. So when we look at a place where two waves are coming together, what we often see is this interference pattern where you have kind of increased intensity and lower intensity, and then increased intensity again. So this kind of overlap of getting bigger and then getting smaller. So that is one wave property to be aware of. And then another property of waves, and this is important to understand as we move towards why this matters for electrons, is that we have something called a standing wave, which is a way of understanding a wave different than other waves. So when we think of like a wave in an ocean, the water itself is moving. So in a stationary wave or standing wave, the wave itself is not moving. A good example of this would be a stringed instrument. So on a stringed instrument, you have a vibration that's occurring, but the string itself isn't moving. It turns out that when we do this, we have a limit to how this works. So on a standing wave, you have 2 points that are specified. So you have a point here and a point here, and those are what we call nodes. So there's special points at which there is basically no vibration going on. And you have to have basically a fixed number of nodes. You can have one node. I guess you could have 2 nodes here, or 1, but you can't have 1.5 nodes. So we can see that here. So we have this wave with fixed here and here, and then here we have an additional node, and an additional one, and an additional one. Okay, so we can see the concept of having a standing wave that has nodes, and those points where there is no movement, as we'll see, can also be important in our understanding of waves when we look at electrons. And then here's some additional examples of wave behavior where you can get a node. It looks like someone had a neat little project here that they wanted to share in this book. So those are some ideas about waves that will be important for then looking at how this relates to electrons and how our understanding of waves has changed related to the discovery of electrons.